Hello, my name's Thanom and I'm from UNSW. Today I'm going to work through some of the MATH1011 calculus questions from the section on numerical integration. So in question 6, there are two parts, but we'll just do part 2, which is about this integral from 0 to 2 of x squared dx. We're asked to use 4 subintervals to approximate the interval, first using Riemann sums, second using Simpsons Rule, and thirdly by essentially using the fundamental theorem of calculus. We'll see that not all of these are actually approximations, but let's start with the Riemann sum, which is certainly going to be an approximation here. 4 subintervals, well, our aim is to find the area from 0 to 2 bound by the graph y equals x squared and the x-axis. So y equals x squared is a parabola, so here's between 0 and 2. My aim is to find this area here. We've got 4 subintervals here, so that's going to divide it into strips of 0.5 width. Now, for our Riemann sum, we're going to be estimating that area using some smaller rectangles, and the question has asked us to use the midpoint as representative points. So the midpoint of this first subinterval here is 0.25, so we'll use that as the representative point, and so we'll be finding the area of this rectangle here. 0.75 is the midpoint of the second subinterval, and so we'll use that as a representative point for the height of the second rectangle. The height of the third rectangle is going to be the function value at 1.25, and the height of the last fourth rectangle is going to be the function value at 1.75. So when we use Riemann sums to estimate an area here, we need representative points for each of the subintervals. In this case it will be the midpoints, and we're going to total the area under the graph. And so we can say that this integral from 0 to 2 of x squared dx, or that area under the graph, is approximately, well, the first rectangle has a base of 0.5, and its height's going to be the function value at 0.25. So f of 0.25 is 0.25 squared. That's the height of the first rectangle there. The second rectangle has a base of 0.5. It has a height of 0.75 squared. The next rectangle has a base of 0.5, a height of 1.25 squared, and the last rectangle has a base of 0.5 and a height of 1.75 squared. So we use the function x squared to calculate the heights of each of these rectangles, and it's the area under the green rectangles that's approximating the area under our blue graph there. Now that value there is 2.625 or 2 5/8. So this integral is approximately 2 5/8 there, using Riemann sums with the midpoint as representative points. Going on to Simpsons Rule, so part B. Now we've got 4 subintervals again, so we're going to need to apply Simpsons Rule twice. So Simpsons Rule has only 2 subintervals, so if we use Simpsons Rule for this first pair of subintervals, what we would be doing is we would be taking these 3 points and estimating the area under the graph by estimating the area under the parabola that goes through these points. Now, the only parabola that's going to go through these points is in fact the parabola x squared. So Simpsons Rule in this case is actually going to give us an exact answer, because we're just finding the area under a parabola here, and Simpsons Rule uses parabolas to in fact estimate areas. So for this first case, so let's write this down. So 0 to 2 of x squared dx. In this case it's going to be exact, just because we've got a parabola here. Now Simpsons Rule says we want h on 3 outside of the first function value plus 4 times the middle function value plus the last function value. So that's using Simpsons Rule for this first pair of strips in here. Okay, so we can only use Simpsons rule for 2 strips at a time. If we use Simpsons rule for this next pair of strips, it's really putting a parabola through these 3 points and estimating the area by the area under that parabola, but we know x squared is the parabola through those 3 points there. So I think I can go over here because the next part won't take me as long. So this is going to be for this, h on 3 outside of the first function value is y on 3 plus 4 times the middle function value plus the last function value there. So that's Simpsons rule for the second strip here. You can, if you like, combine these. So if I take h on 3 out as a factor, this ends up being y1 plus 4y2 plus 2y3s plus 4y4s plus a y5. So you can do that if you wish and combine these two here. So h, remember, is the width of our strips. So in this case, h is 0.5. Each subinterval is 0.5 wide. The y values are going to be the function values. So f of x equals x squared for each of these points, 0, 0.5, 1, 1.5, and 2. So this is going to be 0.5 divided by 3. My first function value is 0 squared, 4 times 0.5 squared for y2, 2 times 1 squared for y3, 4 times 1.5 squared for y4, and a 2 squared for y5. So that ends up being 2.6 recurring, or 2 2/3 for the definite integral here. So usually Simpsons rule would be an approximation because usually we would be using it for functions that aren't parabolas. But if we do apply Simpsons rule to a function that is a parabola, we will certainly get an exact area. Part C, it says just find the exact value by integration. So I think the question means use the fundamental theorem of calculus. So if I want to calculate from 0 to 2 of x squared dx, then the fundamental theorem of calculus says you can just find an antiderivative, so x cubed divided by 3, and then we'll substitute in the limits and find the difference. So 2 cubed divided by 3 minus 0 cubed divided by 3 will give us the definite integral here, which is 8/3, so it's 2.6 recurring, or 2 2/3 there. So you'll notice that this calculation with Simpsons rule gives you exactly the area here. And that makes sense because of how Simpsons rule is defined. Whereas if we use Riemann sums, the area under the green rectangles is only an approximation to the area under the graph, the blue graph of y equals f of x there.